Greetings everyone, my name is Stefan Sorger. I'm an instructor for data analytics and other courses. I'll be taking you through some basic steps for regression analysis using R. We've made every effort to ensure accuracy and relevancy of the content. Nevertheless, we cannot control how the information is being used, so we assume no liability for the use of this information. The purpose of regression analysis is to fit a relationship between the dependent variable and multiple independent variables. Dependent and independent variables go by many different names, as shown on the slide. We can use regression analysis for both descriptive and predictive purposes. Descriptive models capture the average effect of inputs on the dependent variable. Predictive models estimate the dependent variable based on new inputs. We focus on predictive models in this video. In the video, we cover each of the 6 steps in regression analysis, from preparing the data set, to checking the assumptions, to developing linear models based on training and validation data, then assessing the model's performance, and selecting the subset of variables that best predict the data, and using the resulting insight to interpret the results. For this video, we'll use actual real estate data from Zillow.com that consists of house attributes, such as size, for the 94028 zip code in the pricey San Francisco Bay Area. We see a screenshot of the data where rows show records and columns show variables. The data includes several different variables. The dependent variable is price, defined here as price 1000, which is the sales price divided by 1000. The independent variables include potential explanatory variables, such as the size of the house, the size of the lot, the year the house was built, the number of bedrooms, the number of bathrooms, and the neighborhood, a categorical variable represented through dummy variables in the data. The variables represent the data available and may or may not be relevant to predicting house price. Linear regression depends on at least 3 assumptions. We assume that the choice of predictors and form is essentially linear, and that the records are essentially independent. We also want to test for homoscedasticity, where the variation of dependent values does not vary with the values of the independent variables, as shown in the diagram on the left. We want to avoid heteroscedasticity, where the variation does matter. Heteroscedasticity often represents itself in a wedge pattern of data, as shown in the diagram on the right. We read in our data and plot it to check to see if the assumptions are met by plotting it out. As we can see from the plot, the data does not follow the nice, neat straight line pattern found in textbooks. Instead, we see fairly predictable data at house prices less than $10 million. When we exceed $10 million, the data becomes less predictable. We postulate that higher-priced houses tend to be custom-built, intended for a certain market segment, and might not follow typical traits of lower-priced houses. In this video, we felt it was more instructive to display the challenges of working with actual data, with all its faults, rather than hand-picking the data, which of course would make it easier to work with, but not necessarily representative of typical industry situations. Linear regression is categorized under supervised learning. In supervised learning, we partition or separate the data into 2 or more sets. The first set, called the training set, will be used to build the model. We validate or assess the model using the validation data set. We often partition the data into 60% for a training set and 40% for a validation set. In certain cases, we wish to test the validation set using a so-called holdout set. We apply the information to our case example. In order to create our 60% training sample, we take a 60% random sample of the rows of our data. We invoke the sample function in order to take a random sample, with the row names term referring to the rows of the house.df data frame, the dim term referring to dimensions of the data frame, the 1 in brackets referring to rows, not columns, and the 0.6 term referring to 60%. We then use the 60% of the rows we selected to define the training data, which we call train.data. We take the remaining difference of rows of the data frame and assign them to the validation set. To do so, we apply the setDiff function and assign the result to the valid.rows dataset. We assign the data corresponding to the remaining rows to the valid.data dataset. We build our training model using the training dataset. We invoke the LM, or linear model, function to build the linear regression model. We first state the dependent variable, in our case the house sales price, or price 1000, then state the squiggly tilde character to separate the dependent variable from the one or more independent variables. Use a plus sign to separate each independent variable from the other. To be clear, we are not adding the independent variables using the plus operator. If we want to include all the independent variables in the model, we can use the period operator to include all the independent variables as we have done in the example. We also specify the data, in our case the train.data dataset, and get summary statistics using the summary function. The summary statistics show that the model contains only a few significant variables. We see that variables size square feet, representing the house size, and lot acre, representing the size of the building lot, are the only ones to achieve significance with a p-value less than 5%. The only other variable to come close is the variable neighborhood central PV with a p of about 14.6%. We can check the residual values in regression analysis to find the degree of error. To quickly see all the information in one view, we build a data frame which contains the actual values, in this case the home price, the fitted values, in this case from the training set-based regression model, and the residuals, again based on the training set-based regression model. We call the data frame trainRes and print out the first few rows using the head function in R. We can see that the residuals are fairly large relative to the actual price and the fitted values. To build our prediction model from our validation set, we invoke the predict function in R. For the predict function, we use as arguments the linear model based on the training set, or house LM, and the new data, which is our validation data. Just as we did before, we build a data frame we call validRes to show the actual home price values, the values predicted from the validation set, and the residuals. Again, we see that the residuals are fairly large relative to the actual price and predicted values. We estimate the accuracy of the model using the accuracy function from the forecast package in R. To do so, we start by loading the forecast library and then invoke the accuracy function, specifying the fitted values from the training model and the actual data from the validation set. We predict values based on the model and the validation data, then calculate the accuracy of the prediction as compared to the actual data. The accuracy function output includes the root mean square error, or RMSE. We note that the RMSE errors for both the training and validation data are fairly large relative to the actual values. The variable subset selection process identifies the most significant variables, similar to us pouring in all the variables in a model into a funnel and filtering out all but the most effective ones. The specific algorithm we demonstrate here is called backward elimination. We invoke the step function for stepwise regression, stating the initial model as the object, which is usually the fitted model created by the training data set, as well as the direction, which we define as backward in the case of backward elimination. The variable subset selection process lists out only 3 significant variables out of the original 8. The first 2 significant variables are size square feet, the size of the home, and lot acre, the size of the building lot. The third variable is membership to the central PV neighborhood, or NA central PV, which barely made the cut, having achieved a p-value of 4.7%, just below the 5% limit. the RMSE is still large relative to the actual value. Surprisingly, the RMSE is actually less now with fewer variables than in the full model. The results suggest that we can improve the model, such as selecting a different, more relevant set of variables. In this video, we covered the process of linear regression analysis, from preparing the dataset to checking our assumptions, to partitioning the dataset into training and validation datasets, to creating the training model and assessing its performance. And we ended the video with the variable subset selection process and interpreting the results. Thank you for watching. If you found this video helpful, please subscribe to the channel.